Welcome to the first lesson of Module 3, Digital Solutions for Energy Efficiency in Data Centers. In the previous module, we explored physical and architectural strategies for reducing the energy footprint of data centers, from optimizing IT utilization to improving cooling and sustainable infrastructure design. In this module, our focus shifts to digital solutions, tools that leverage real-time data, automation, and artificial intelligence to achieve energy efficiency. The starting point for any digital strategies is monitoring. A modern data center generates an enormous amount of data: power draw, temperature, humidity, air pressure, workload distribution, and equipment utilization. By collecting and analyzing this data, operators can clearly see how the facility uses energy, where waste occurs, and how different systems work together. Energy monitoring involves deploying a network of sensors across servers, racks, cooling system, and power distribution units, collecting real-time information. These data are fed into the data center infrastructure management systems, which integrate data across the IT and facility layers, offering a comprehensive view of operations. More advanced platforms also allows for real-time data visualization, alarms, and predictive analytics, enabling operators to anticipate problems before they occur. This data provides the basis for calculating key metrics like the PUE. By tracking PUE continuously, operators can detect anomalies such as sudden increases in cooling demand or underutilized servers drawing idle power. Beyond static monitoring, predictive maintenance represents the next step. Traditional maintenance follows fixed schedules or responds to failures. Both approaches have drawbacks. Scheduled interventions may replace parts before necessary, wasting resources, while reactive maintenance risks downtime or equipment damage. Predictive maintenance instead uses data and algorithms to forecast when components are likely to fail or degrade, enabling interventions exactly when needed. For example, cooling system performance often declines gradually due to the clogged filters, pump inefficiency, or refrigerant leakage. By continuously monitoring parameters such as airflow, pressure differentials, and energy draw, algorithms can identify early signs of degradation and trigger maintenance alerts. In the IT layer, predictive maintenance can monitor servers for anomalies in power consumption or thermal behavior. A sudden rise in idle power draw might indicate a failing power supply, while repeated thermal spikes could suggest a malfunctioning fan or poor airflow. Identifying these issues early allows for proactive replacement, avoiding energy waste and unexpected outages. The effectiveness of predictive maintenance relies on machine learning. Algorithms are trained on historical data that learn to distinguish normal operational patterns from anomalies. Over time, they improve in accuracy, reducing false alarms, and enabling increasingly precise forecasts. Beyond operational reliability, monitoring and predictive maintenance have a direct impact on energy efficiency. By ensuring that systems operate at optimal condition and avoiding degraded performance, facilities can minimize wasted energy. Studies suggest that predictive maintenance can reduce energy consumption in cooling and mechanical systems by 10–15%, while also extending equipment lifespans and reducing unplanned downtime. In summary, monitoring and predictive maintenance represent the foundation of digital energy efficiency strategies in data centers. Monitoring provides visibility into operations, enabling operators to understand where energy is consumed and where inefficiency arises. Predictive maintenance builds on this data, using analytics to forecast failure and optimize interventions. Together, they reduce energy waste, extend the equipment life, improve reliability, and support both operational and sustainability goals. In the next lesson, we will go a step further, looking at how artificial intelligence can move beyond the prediction to optimization, automatically adjusting systems in real time to achieve the best possible balance between performance, reliability, and efficiency.